Hello students, welcome again. Let's start today's session with topic electric potential energy of electric dipole in an electric field. So actually we will be placing the dipole in uniform electrostatic field, and what amount of work done is there by the externally applied torque, that will be the electric potential energy there in the electrostatic field. So for the definition, what can we say? Electric potential energy at a point inside the electrostatic field is the amount of work done in rotating the electric dipole from its zero energy level to a certain position, making an angle say theta with the electrostatic field. So that is called electric potential energy. So let's proceed calculating this. So for that, suppose we have uniform electrostatic field being represented by these parallel equidistant lines. Suppose this is electrostatic field, and the perpendicular to this field will represent the zero energy position of the electric dipole, where from the dipole will be rotated. Suppose this represents zero energy position of the dipole. So here from this position, suppose the dipole is rotated and is brought to this position, making an angle say theta with the electric field. So here actually this is the electric field direction, and this is the dipole moment direction, and this is the angle made. Say this be negative charge, this be positive charge of dipole. So the forces acting on these oppositely charges of dipole are plus QE along the direction of this electric field, and minus QE just opposite in direction to this electrostatic field. Now here actually when this dipole is rotated from this zero energy position to this theta position, then certainly the electrostatic field will apply the torque, restoring torque, in this displaced position of dipole, which tries to accelerate the torque. But we need to keep this, or we need to bring this dipole to this final position from this position in the electrostatic field. So we need to apply equal amount of external torque so that there is no acceleration, angular acceleration produced in rotating the dipole in the electrostatic field. So that externally applied torque will be say tau external on this dipole. Now suppose we assume that this dipole is rotated through very small angle d theta, and now in producing that d theta angular displacement in this dipole in electrostatic field, let's say the work done is dW. So let's calculate that. So here we start the torque acting on dipole held at theta angle with electric field E. Let me write it with vector. So we write now vector tau equals to vector P cross vector E. Now magnitude wise, what can you say? Tau equals to PE sin theta. Now suppose dW amount of work is done to produce d theta angular displacement in the dipole. So let's calculate that. Let dW be the work done in rotating the dipole by d theta angle. Therefore, dW is given as tau external d theta. So here tau external will be just equal to this, and that we are writing now PE sine theta d theta, that's dW. Let's calculate total work done by integrating this equation on both the sides, taking the limit from 0 to theta. So the total work done in rotating the dipole from theta equal to 0 to theta equals to, say, theta. Actually, it's not 0. Try to understand. This is 90 with electric field. So you write now it 90. So here, we now when get left hand side gets integrated, we get work done, and since PE will be uniform, so we are writing it out of the integration, and it is from 90 to theta sine theta d theta. So let's proceed. When this gets integrated, we get minus cos theta, and here it is 90 to theta. So just placing now the limit PE, it's minus cos theta, minus plus cos 90, and the cos 90 is 0. So we get minus PE cos theta, and this work done is nothing but what? Electric potential energy. So we represent it by U. So U now is minus PE cos theta. So this is the desired outcome. So let's have few special cases how this last result obtained changes when we consider the stable equilibrium position of dipole and when we take unstable equilibrium position of dipole. So let's have few special cases. So for the first case, when theta equals to 0, when our dipole moment is parallel to electrostatic field. So under that condition, we have theta to be 0. Therefore, we get that U equals to minus PE, and that is cos 0. Cos 0 is 1. So we get minus PE, and this corresponds to the stable equilibrium. Remember, this we have already read it. So this corresponds to the stable equilibrium of dipole. Okay, now let's discuss case 2. When the dipole is held at perpendicular, when dipole moment vector is perpendicular to electrostatic field, that is theta is 90 degree. So if this cos 90 is taken, so this makes U to be 0. So we get U equals to 0. Let's discuss case 3. When dipole is held anti-parallel to electrostatic field. That is, theta here is 180 and cos 180 as we take, it gives -1, and that minus and this minus becomes plus. So we get maximum potential energy, and that's plus PE, and this corresponds to unstable equilibrium. Unstable equilibrium position, this corresponds. Okay students, let's move on. So let's start second topic, work done in rotating an electric dipole in an electric field through an angle. Here actually the dipole will be placed as done in previous topic, uniform electric field, and in that electric field we will not consider the zero energy position, rather we will consider the dipole is already kept at certain angle initially with the electric field, and now from that position the dipole is rotated to the next angle position. And now what is the work done, that is to be calculated here. So as we have seen, when the dipole is rotated from its previous position to the next position in the electric field, so there is the torque being applied by the electrostatic field, and that torque now accelerates the displaced position of dipole to the previous position, and we want that dipole to get rotated along the direction we want or we desire. So just to rotate that from its initial to final position, we need to apply an equal amount of external torque on the dipole so that there is no acceleration produced, and hence that externally applied torque now produces or does work on the dipole. So let's calculate that. So here to start with, we say work done in rotating the dipole through d theta is given as dw equals to tau external d theta, and here tau external is what? PE sin theta. So let's place PE sin theta d theta. Now integrating both the sides, we can get total amount of work done. So the total work done W is equal to integral from, here actually we are taking angle 0. It means the dipole is originally at the position parallel to the electric field, that is theta is 0. So here it is 0 to a certain angle, say theta. Else you can go for taking this as theta 1 and this as theta 2 as well, and later on taking theta 1 to be 0 and theta 2 to be theta. So here you write PE sin theta d theta, and here we get PE minus cos theta as the integration of sin theta. Limits would be from 0 to theta. So just having this PE, now cos theta minus plus cos 0. So cos 0 is 1. So we get PE into 1 minus cos theta. So this is actually the desired result. So let's have few special cases here. Special cases. Suppose for the first case, if P is parallel to E So in that case, actually here, suppose P is perpendicular to E finally. Okay. So we are now rotating the parallelly placed dipole to the perpendicular position of the dipole in the electrostatic field. So here actually the result would be W equals to PE 1 minus cos 90 would be 0. So this is PE plus. Now for second case, if dipole moment is anti-parallel finally to vectory, that means initially the dipole is kept parallel, theta equal to 0, and finally we are rotating it to the position anti-parallel to the electrostatic field, that is theta equals to 180. If you are taking theta 1 and theta 2, so you must consider theta 1 to be 0 and theta 2 to be 180. So this result now transforms to W equals to PE cos 1 minus 1 cos 180 is minus 1. So this is 2 PE. So this actually condition sometimes gets asked in CBSE examination, that calculate the amount of work done in rotating the dipole from its stable equilibrium to an unstable equilibrium. So stable equilibrium student position is what? When theta is 0, that is dipole is parallel to electrostatic field, and when it is rotated to unstable equilibrium, that is theta is 180 finally. So under that condition you should consider this case and reach at this result 2 PE. Okay, so let's move on. Let's have few numericals based on the concepts that we have gone so far. So the first question that we are taking now today, the potential at a point small x measured in micrometer due to some charges situated on the x-axis is given by Vx equal to, first question, Vx equal to 20 upon x square minus 4 volt at some position, at some distance from the source charge. Potential is given to be this. What is the electric field E at x equal to 4 micrometer? At this position we need to calculate electric field. So students, remember the relationship between electric field and electric potential. So let's start. Since we have E to be equals to minus dV by dx, isn't it? Later on, just placing this value of V as 20 upon x square minus 4, let's have differentiation of this. 20 is constant, minus 20 d by dx of x square minus 4 whole pass to minus 1. So when we just differentiate it, we get plus 20 into 1 upon x square minus 4 square, and when x square gets differentiated you get 2x. So finally you get 40x upon x square minus 4 square, and now students this x is given to be 4. So let's calculate electric field directly by placing x as 4 here, the final outcome. So therefore electric field intensity that we will be getting, 40 times x is 4 upon 4 square minus 4, then this square, and students when you just solve it you'll be getting 1.11 volt per micrometer. So this will be the desired outcome for this question. Let's move on for the second question with us. Question number 2 we are having now. Calculate the voltage needed to balance an oil drop
carrying 10 electrons when located between the plates of a capacitor which are 5 millimeter apart. Plates are 5 mm apart. Given mass of drop to be 3 into 10 powers to minus 16 kg and charge on electron that we are aware of. Now here actually the weight will be balanced by the force given by the electrostatic field. So here let's start. We will be saying that QE will be just equals to mg, and here we want to calculate voltage needed to balance. Now electric field is related with potential, so that relationship is V upon R, which is equals to mg. Now here actually this voltage needs to be calculated, so you just cross multiply rest of the things. So mg R upon Q. Now everything is given to us. So let's place the values here. So we have mass to be 9 into this mass is 3. So this we have 3 into 10 powers to minus 16. This is given to be mass into gravity. We are having 9.8 into separation. Small r is given to be 5 mm. So 5 into 10 powers to minus 3. So this is the value of this distance. Separation between the plates of capacitor. Now charge on electron 1.6 into 10 powers to minus 19. Okay students, so work out in solving this. So you will be getting approximately finally 9.19 volt as the answer. So check it. Okay, let's move on students. Let's have third question now. An infinite thin plate sheet of charge density 10 powers to minus 8 coulomb per square meter, sigma to be 10 powers to minus 8 coulomb per square meter, is held in air. How far apart are two equipotential surfaces when potential differ by 5 volt? Potential difference between the surfaces is given to be 5 volt. Now you need to calculate the separation between them. So let's start. Electrostatic field is of sheet that we are aware of, thin plane sheet, equals to sigma upon 2 epsilon naught, and this P is related with potential. So let's write the potential this to be delta V upon delta X. This is the relation of electric field with potential gradient, I must say. This is sigma upon 2 epsilon naught. Now we need to calculate separation, so you just bring this and rest of the things there. So you get delta V into 2 epsilon naught upon sigma, which is delta X. Now everything is given to us. Delta V potential difference is 5 volt given in the question. Now 2 epsilon value 8.85 into 10 powers to minus 12 upon this sigma is given to be 10 powers to minus 8. Okay students, you just go on solving it. You'll be getting approximately 88.5 into 10 powers to minus 4 meter, or you can say 8.85 mm. This will be the separation. So let's move on for the next fourth question with us. So fourth question, I'm just reading it out. A molecule of a substance has a permanent electric dipole moment equal to 10 powers to minus 29 coulomb meter. A mole of this substance is polarized by applying a strong electrostatic field of 10 powers to 6 volt per meter. the direction of this field is changed by an angle of 60 degree, estimate the heat released by the substance in aligning its dipoles along the new direction of the field. For simplicity, assume 100% polarization of the sample. So this is the question. Okay, so let's move on. We'll be writing initial potential, electric potential energy. So U initial will be equals to number of moles into PE cos theta. So cos is 0 initially. So here actually we will be writing this N to be equals to whose number it is, and final potential energy will be writing N into PE into cos. Finally it is brought to 60 degree angle position. So the loss in potential energy will be equal to both for what is the estimate the heat, and that work done will be the heat released. So you just write heat released equals to loss in potential energy. So this is simply Ui minus Uf, and you now place NPE into cos 0 minus cos 60, and when you just place the value 6.023 into 10 past 223, the value of Avogadro's number P is given to be 10 past 2 minus 29, and this E is given to be 10 past 2 6. This is 1 minus cos 60 is half. So students, work out for the solution. This will be approximately 3.011 joule. So check this. Okay, so let's move on. Let's have fifth question. A conducting spherical bubble of radius small a and thickness small t in such a manner that thickness is much smaller than radius is charged to potential capital V. That is, the potential of spherical bubble is given to be V. Now it collapses to form a spherical droplet. Find the potential of the droplet. So let the potential of the droplet be V dash. So here the volume will be same. So we have volume and charge conservation we will be using here. So for the fifth question solution, we are writing the volume of droplet finally. Droplet 4 by 3 pi r cube, and the volume of that spherical bubble. So 4 pi small a square, radius is given to be a, into that thickness. So here from you just work out and find the radius. So here it is 4 pi gets cancelled, and we get r to be equals to 3. This r to be equals to 3a square into t whole past to 1 by 3, as we have cubic root on both the sides. Just cross multiplying this and taking cubic root on both the sides, you'll get this. Now according to charge conservation, charges are also conserved. Therefore we are writing the charge on bubble 4 pi epsilon naught into r into this V dash. This is the charge on droplet. Yeah. Now charge on bubble. So charge on bubble will be written as 4 pi epsilon naught into radius is given to be a and is charged to a potential V. So here from you just cancel out this 4 pi epsilon naught, 4 pi epsilon naught, and let's have the V dash value, and that V dash will be equals to V upon R. So here V upon R into this A will also be there. So you just place A here and place the value of this.
So you get K upon R is 3A square T pass to 1 by 3 into V, and finally you reach at V into A upon 3T whole pass to 1 by 3 as your answer. Okay students, so let's have seventh question. Two equal charges 2 into 10 pass to minus 7 coulomb each are held fixed at a separation of 20 centimeter. A third charge of equal magnitude is placed midway between the two charges. It is now moved to a point 20 centimeter from both the charges. How much work is done by the electric field during the process? That needs to be calculated. So let's move on. Question number 7. So here I must draw a diagram first that you can have better understanding of the question. Suppose here charge 1 2 into 10 pass to minus 7, the similar charge 2 into 10 pass to minus 7 with initial separation of 20 centimeter is given. Now midway here at point A, another similar charge is kept. Now finally it is moved to 20 centimeter from each of the charges. So this position, final position of the charge B of same magnitude is at same 20 centimeter separation from both. So here we need to calculate the both the magnetic electric field. So let's start. When the charge is at A, when the charge, this charge final position is here initially, then we write U1 to be equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R plus Q2 Q3 upon again R. So here actually this is Q1, this is Q2, this is Q3. So 9 into 10 pass to 9 into this 2 into 10 pass to minus 7, Q1 Q2 are same. So there will be a square upon 0.1, 10 centimeter, 10 centimeter, half of 20 centimeter, plus the same term 2 into 10 pass to minus 7 square again upon 0.1, again the same distance 10 centimeter. So students, just solve it. You will be getting 72 into 10 pass to minus 4 joule with you. Now let's calculate when the charge is brought to finally B. When the charge is at B, so you write U2 which is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R plus Q2 Q3 upon again R. This time it will be 9 into 10 pass to 9, 2 into 10 pass to minus 2. The same magnitude of charge is given which is placed here. So it will be a square upon 20.2 plus the same term 2 into 10 pass to minus 2 square upon 0.2. So students, just work out and simplify this. You will be getting 36 into 10 pass to minus 4 joule. Finally this, let's calculate the change in potential energy. So here the work done will be equals to the change in potential energy, and that will be U1 minus U2, and that will be 36 into 10 pass to minus 4 joule. That minus this will give you this. Okay, let's move on. Okay students, let's have question number 8. An electric field, let me write that value. Electric field E equals to 20 I cap plus 30 J cap Newton per coulomb exists in the space
if the potential at the origin is taken to be 0, find the potential at the distance to be given is 2 meter coordinates are given, so that will be written as 2i cap plus 2j cap. So this is in meters. Okay, so we have to calculate potential, and potential gradient is related with electric field. So directly let's write V equals to minus vector E dot vector R. So here vector E is 20i cap plus 30j cap dot 2i cap plus 2j cap. Have the cross multiplication. So you will be having 40 plus 60 minus, and this will give you minus 100 volt as your required answer. Fine with this, student? Let's move on. Let's have question number 9. An electric field of 1000 Newton per Coulomb. Electric field of 1000 Newton per Coulomb is produced between two plates having a separation of 2 centimeter. Separation of 2 centimeter. Now, as shown in figure, and the figure is, these are two plates, and this is the separation of 2 centimeter. Electric field exists from bottom to top. Now, first to calculate what is the potential difference between the plates. Potential difference between the plates. Second, with what minimum speed should an electron be projected from the lower plate in the direction of the electric field so that it may reach the upper plate? With what speed the electron should be projected from here so that it reaches to upper plate? This is the second question. Now third question is, suppose the electron is projected from the lower plate with the speed calculated in second part. Suppose the speed that we will be calculating in the second part of the question, with that speed the electron is projected right from here, then the direction of projection makes an angle of 60 degree. It's not vertically projected, rather it's projected at 60 degree with this plate electric. Then find the maximum height reached by the electron if it goes at 60 degree angle. So what is the final height that it reaches? That needs to be calculated in third part. So let's start solving it. So for the first part I must write, first part, since we have V equals to E into dl, so here actually E is given to be 1000, and the value of this dl with us is given to be 2 upon 100. So this way these two gets cancelled, it gives us 20 volt second. Now second part of the question, we need to calculate speed. So for that we must have acceleration, so that we can go for the third equation. So A equals to F by M will be using, and F will be the force due to electrostatic field, QE by M, and let's write the values. 1.6 into 10 powers to minus 19 charge on electron. Electric field is 1000. I'm writing 10 powers to 3 upon 9.1 into 10 powers to minus 31. So students, just work out and find out the value of A, and this you might be getting perhaps 1.75 into 10 powers to 14 meter per square second. And finally C, here the initial speed with which the electron will be projected, let it be u, and finally when it reaches to the upper plate the final velocity becomes 0. So let's use third equation. V square minus u square equal to 2 into A, 1.75 into 10 powers to 14 into S. S is how much? 2 centimeters. So it's 0.02 meter. So students, just take the square root on both the sides. So you will be getting 2.64 into 10 powers to 6 meter per second. as the answer for second part of the question. Now, for the third part of the question, if say the electron is being projected with this speed at 60 degree, then what is the final height that it reaches? It needs to be calculated in the third part of the question. So here, actually everything will remain same, and we'll go for the third equation. So 0 square minus, instead of now we will be taking u cos 60. Okay, when u gets resolved, so we'll be having u cos 60 square equals to 2as. This needs to be calculated, so you just bring 2a here. So u square cos square 60 will be 1 by 4 perhaps upon that 2a, which is equal to s. Now placing the values, we will be having this u to be 2.64 into 10 power to 6 into 1 by 4. Actually its square will be there upon 2 into a is given to be 1.75 into 10 power to 14. So students, just work out and try to obtain the final outcome. Perhaps you'll be getting 0.497 into 10 power to minus 2, or you can say 0.50 mm. Not mm, it will be in centimeters. So rounding it off, 0.50 centimeter. It's in meter. Okay, let's move on. Okay, students, so let's have question number 10. The kinetic energy of a charged particle decreases by 10 joule as it moves from a point at potential 100 volt to a point at potential 200 volt. Find the charge on the particle. It's quite simple. Change in potential energy will be equals to change in kinetic energy will be equals to work done, and that work done will be equals to change in potential into test charge. So this will be the approach. So I must write question number 10 here, and delta K, as I said, it will be equals to W. And this W, as I said, change in potential 200 minus 100 into test charge Q naught, and Q naught we need to calculate, and change in potential is given to be 10 joule. So you just have this 100 so 10 by 100 will be equals to Q naught, and this will give you 0.1 coulomb as your answer. Quite short, no? Okay. So let's have next question, finally 11th number. Two identical particles, each having a charge of 2 into 10 power to minus 4 coulomb and mass of 10 gram, are kept at a separation of 10 centimeter and then released. What should be the speed of the particles when the separation becomes large? So let's proceed. Let me draw the diagram so that we may have better understanding. Charges given are 2 into 10 power to minus 4 coulomb, 2 into 10 power to minus 4 coulomb, and the separation is 10 centimeter. So here you just first find out force, electrostatic force acting between them at this separation, and later on we'll be calculating the acceleration produced. So you write now force equals to 1 upon 4 pi epsilon naught q1 q2 2 into 10 power to minus 4 square upon distance square. So this is 10 into 10 power to minus 2 its square. And when you just solve it, 9 into 10 power to 9, taking this value, so you will be getting 36 into 10 power to 10 power to 3 perhaps Newton. This will be your force. Now let's find out acceleration, dividing this force by m. So A will be equals to F by m.
and this 36 into 10 power to 3 upon mass is given to be 10 gram. So 10 into 10 power to minus 3 in kg. So you'll be getting 36 into 10 power to 5. Okay, so now we can have what should be the speed. So let's apply the third equation. So we have now v square minus u square equals to 2as. Now when these are taken, initially they are at rest, final speed we need to calculate. So v square minus 0 square equal to 2 into a is 36 into 10 power to 5 into s is 10 centimeters, so 10 into 10 power to minus 2 in meter. So now let's have the solution of this so that we can have the answer. Taking square root on both the sides, we can have v, and that v now will be equal to 8.485 into 10 power to 2 meter per second. So this is the final answer, students. I hope you might have enjoyed today's session. So it's the end of today's session. Do like and subscribe the channel.